Alright, so we are going to do a screencast on gravity. Before we begin, I want you to read through these true-false questions in your notebook. Put numbers 1, 2, and 3 and answer these to the best of your ability. Pause the video while you do that. Okay, welcome back. We are going to review these questions tomorrow in class, but I wanted to see if you can answer these questions by the time you have finished watching the videos that I have posted. Today we're going to look at Newton's universal law of gravity. You will be able to describe Newton's historical impact and use his universal law of gravity to determine the force and behavior of various objects. Why do we have to learn this? Well, think about something like the invention of the wheel. How did that change humanity? Or think about the Revolutionary War and the creation of the United States. How did that affect global society? Or the atomic bomb? Or the attack on the Twin Towers? Or the cure for cancer? How has that changed? Oh, wait a minute, we haven't cured cancer yet. But imagine if we had cured cancer. Imagine if there was a cure. There would be a time before the cure and a time after the cure, just like with all those other things, a time before the bomb and a time after the bomb. These single events that I just described or just showed are transformative in human history. Well, Newton's publication of his Principia is one of those events in history, where before that life was one way. After the publication of the Principia, it completely changed the way we view our universe and the things that we were able to do. You see, before Newton, we had over 2,000 years of Aristotle's thoughts, or a couple, not quite 2,000 years, about 1,800 years of Aristotle. And basically, the guy was very, very smart. He was leading philosopher. He was a politician. He was a scientist of sorts. And basically, because of his incredible genius, his word became the authority. So for over 1,000 years after Aristotle's death, people kept believing the things that he said, even though some of the things that he said were wrong. They would say it with the justification of, well, Aristotle said, and if Aristotle said it, then it had to be true. Well, he was a great philosopher, a great politician, but not a very good scientist. Many of the scientific conclusions he came to, he did through thought and not through experiment. And it was Newton who, through experimentation, discovered some of the realities that we live with now. But I'm going to take you to one of his thought experiments. This is Newton's thought experiment with this idea of if you are on top of a very tall mountain and you shoot a cannonball, it's going to fall to the ground. If you shoot that same cannonball with a higher velocity, it's going to go further. All right, so this is obvious. But if you take the curvature of the Earth into account, if you shoot that cannonball with a high enough velocity, it will be falling, but it will never actually hit the Earth. It will just forever be falling as it goes around the Earth. And he realized that this is the force that causes the moon to orbit the Earth. The moon is attracted to the Earth by the force of what he called gravity. So this is a centripetal force. It's also the force of gravity pulling the moon towards the Earth. But the moon also has a tangential velocity. And so because of that tangential velocity, it is forever orbiting the Earth. What if I concocted an evil plan where I wanted to destroy the Earth, or my evil plan to destroy the Earth? I could do that by taking away the moon's velocity. If I took away the moon's velocity, well, the only thing we'd have is the force pulling the moon towards the Earth. So what would happen? Well, the moon would, of course, get pulled towards the Earth, crash into it, and eventually blow it up. So this is Newton's major contribution. Besides his laws of motion and optics and all these other things that he contributed to, he gave us the universal law of gravity, where the force that causes the moon to go in orbit around the Earth is exactly the same force that causes an apple to fall from a tree. You might think, well, why is that so mind-blowing? Well, Aristotle had said there are laws that govern nature here on the surface of the Earth, and then a completely different set of laws that govern the heavens, that govern the motion of the moon, the sun, the stars, everything that we see above the Earth. But he was wrong. One of Newton's great contributions is that the same laws that govern life here on Earth are exactly the same as the laws that govern all of the universe, hence the name universal law of gravity. In formula form, here is the universal law of gravity. Mass 1 times mass 2 divided by the distance between them will cause those two objects to have a force. Well, really, it's the masses of the objects that cause the force, and the force also depends upon how far apart they are. So if the objects are close together, the force is large. If the objects are far apart, the force is weak. However, there's something wrong with this equation. I want you to pause the video, see if you can figure it out. Alright, so I'm hoping you paused, tried to figure out what is wrong with this equation. As I've said before, units are important. So what are the units on this side? We have a kilogram times a kilogram divided by meters squared. What are the units on this side? It's a newton, which is not equal to a kilogram times meters squared, or divided by meters squared. There's a missing part to this formula. The missing part is the universal constant, the gravitational constant. So this is the complete formula and the definition of everything there. My recommendation is you write all of this down. And then we're going to do some sample problems. And an interesting result of this formula is that it's telling us that if any two objects in the universe have mass, and they are attracted one to the other, there is a universal force that is attracting every mass to every other mass in the universe. So let's do a very simple calculation where, let's say, you and a friend are floating out in the middle of nowhere, in the middle of space. There's nothing else around. There will be a force of gravity that is attracting the two of you. So let's do the sample calculation here. We are going to use Newton's universal law of gravity. F is equal to G, m1, m2 over the distance squared. Let's enter that directly into the calculator. We have G, which is 6.67 times 10 to the minus 11. My suggestion is that you use the second EE function on your calculator. Don't do caret negative 11. You're going to need to do second EE and then negative 11. Use that for G. Multiplied by 70 kilograms, multiplied by 70 kilograms, divided by the distance between you squared. The distance between you is 5. Square that. That gives us an extremely small force. But this is the right number. 1.3 times 10 to the negative 8. The force of gravity that would exist between you and your friend would, in fact, be very, very small, because your masses are pretty small. But eventually you would float together. That's just what would happen. Let's do something with a slightly bigger mass, like the mass of you and the mass of the Earth. The distance from the center of you to the center of the Earth is really the radius of the Earth. We're going to use the mass of the Earth and the mass of you. So let's go back to our calculator, try this out. So G, 6.67 times 10 to the minus 11, multiplied by the mass of the Earth, 5.98 times 10 to the 24, multiplied by the mass of you, divided by the radius of the Earth, 6.37 times 10, times 10 to the 6 meters. This will tell us the force of gravity between you and the Earth. Oh, there's something wrong. Oh, I forgot to square. The radius has to be squared. So, I got a value of 688 newtons. 690 newtons. Does this make sense? Well, what's another way to calculate the force of gravity between you and the Earth? Fg equals mg. 70 times 9.81 gives us pretty much the same number. So, one that I want you to try on your own. I'll collect this tomorrow. Force of gravity between you and the sun. Calculate it. And you should come up with an answer that makes sense. Think about this. Will the force of gravity between you and the sun be bigger than or less than the force of gravity between you and the Earth? Create a reason, a justification in your own mind before you do the calculation. Do the calculation. See if the answer agrees with what you thought. And that's all we have. In summary, Newton's historical impact, he changed the way we view our universe. When we look at stars, or planets orbiting other stars, or a nebula halfway across the universe, we think we understand what's going on because the laws of nature that govern the behavior of those things are the same as they are here on the Earth. He also gave us the laws of motion, gave us a universal law of gravity, and yeah, that's it. Okay, we'll see you in class tomorrow. Take care. Bye.